So we have seen in creep how dislocation climb can happen, and this we have discussed in the dislocation chapter also before. So if you have a dislocation, let's say edge dislocation here, then you need a vacancy so that this atom can go somewhere else. And this atom then acts as an interstitial or substitutional, depending upon the atomic size. And then once you have, so let me use the pointer. So once this atom is out and you have a vacancy here, then this dislocation has climbed. So this mechanism we know, and this happens at lower temperature. Okay. So that was the mechanism of dislocation climb, which happens in creep. And then we also discussed about grain boundary sliding. So for example, in this diagram, you have 3 grains. And when these grains will slide, then because of the creep deformation, you can have a void creation at the node of the joining of these 3 grains. And this is another mechanism, as you can see in this picture also, which creates damage under creep deformation. So we have discussed stress rupture test, where we load the specimen at certain stress, and then we keep the specimen until it fails. So if you plot rupture time versus different amount of stresses, then you may find a straight line, or you may find a change in a straight line with a slope, which describes a change in activation energy. So the mechanism is changing, and that's why the slope changes. This part also we have discussed. And when we plot the rupture time versus the stress, we have to do a lot of tests, and you can then plot. So here you see in this plot, you have LN316, you have FR316, which is a different grade of 316, is a stainless steel. And all of these are different grades of the same steel, which is used in different places. So they must have different amount of impurities and different amount, a little bit of heat flow will also, so the manufacturing will be different. It's called the heat. So for example, if you make one sheet or one billet out of or one slab out of a caster, so one heat, that means so you make steel either by electric arc furnace, or you make steel by uh, Linz Donawitz furnace, or LD furnace, or basic oxygen furnace. And so in one go, the amount of steel you make is called one heat. And that usually has same chemical composition. But in the next heat, even if you are making the same material, composition may differ a little bit if you are not doing secondary refining process of the steel. So these are different heats of a steel. That is why you have different data, and you do the testing at different stresses, and you keep the specimen until the failure time, and you plot this, and you have done it. So this data has been done at constant temperature of 873 Kelvin, and you get the stress rupture profile from this. So this is the plot for the stress rupture profile at different temperatures. For, see, you have different heat here, then you have MIT heat, which is a different number, and these data are for S590 grade of steel. So you see that the different heats are giving you different profiles. So a little bit different, but they still follow the straight line. And the difference is because they are produced by the different heat. And if you do it at different temperatures, depending upon the activation energy, so the mechanism, if that is changing. So for example, in this plot, there are changes in slope 2 times. Whereas in this case, in this line, you have the change in slope only once. So at this temperature of 650 degrees Celsius, you only have one change in mechanism, whereas at 1040 degrees Celsius, you are seeing that there are 2 times change in mechanism. So then if we see, and we have discussed the Larson-Miller parameter also. So here the Larson-Miller parameter versus the stress is plotted, and we have discussed an example also in the last lecture, that you calculate the Larson-Miller parameter. So for example, 100,000 hours, and you want to know that at which stress the material will fail. So you calculate the Larson-Miller parameter, and you find out the curve from some amount of data, and then you can even find somewhere in between where you have not done the experiment. So this works well for extrapolation or for a long time test if you want to avoid it. Then this is again the Larson-Miller parameter plot for different grades of steel, and you see that all of them are showing one band of curve, and that is why it is called master curve, because uh, as long as you are not changing the material completely, the curve usually is same for all types of, all different grades of steel. So you see there is a variation of 12 chromium steel, and then you have a steel which does not have any chromium, then you have a steel where you have 1% weight percent of chromium, and you still are getting the data in the same band. Okay, so now we will discuss the mechanism of creeps, what happens at different stress levels and different temperatures. So if you are at lower temperature, then you can have, you will have dislocation glide. So you will have, so what happens in this case is that dislocations are getting blocked, let's say at lower cortical barrier or at dispersion, and they need some amount of energy to cross that barrier by using Urovon's mechanism, for instance. So in Urovon's mechanism, you don't need a climb process to happen. And therefore, that process is not based on the non-conservative movement of dislocation. So it is just that a little bit of thermal activation is required, and the dislocation can either cut through it, or it can pass through the barrier, or it can break the barrier. And that kind of creep is called dislocation glide. So that mechanism of creep is called dislocation glide. It happens when the stress by shear modulus ratio is greater than 0.01. So this is a high level of stress in comparison to other mechanisms. So this is happening at higher stress but lower temperature. Dislocation creep mechanism happens at a comparatively higher temperature. So here non-conservative movement like climb happens, and dislocations can climb up from the barriers, and they can move. And the stress range is smaller than what you have here. So this is in the range of 10 to the power minus 4 to 10 to the power minus 2. So the ratio of sigma divided by G is in this range, but the temperature is higher. Then, so this mechanism is dislocation creep. Then you can have diffusion creep, where the vacancies and interstitial, they flow in order to have the complete material flow of the material under the load. And this happens at even higher temperature, but the stress by shear modulus ratio is very small. So it is less than 10 to the power minus 4. If you go further higher in temperature, then grain boundary sliding occurs. Harper down creep is not important at this point of time. It is uh, it happens at a very small value of stresses. At a very low stresses, there is a different mechanism of creep, which was named Harper drawn creep, but that is not practically important. So we will not discuss that in much detail. So basically, if you see the steady state, so second stage creep rate, that can be described by a power law relation. So again, we have a Arrhenius type equation where we have an activation energy and temperature, and then you have the influence of stress on it, and this is normalized by a reference stress, which produces a strain rate of a constant value. So let's say epsilon dot, that is the value of the reference strain rate. So it of course depends that which value of strain rate you're choosing as the reference stress, and that will change the equation. But if you keep it constant, then it follows this kind of power law relation, and this is important for the steady state creep rate. So n is the creep exponent and a is the constant, and you can find out by taking logarithm, doing the experiment at different stresses. But this will require you to do creep testing because you want to find out the minimum creep rate. Okay, so this equation you cannot find out by doing stress rupture test. So diffusion creep, as we discussed, can be divided further in different mechanisms, because diffusion can happen through different places of the microstructure. So for example, diffusion can happen from the lattice, so from the grains, and that usually happens at comparatively higher temperature. Okay, so if the temperature is high, atoms are able to diffuse even through the grains. So here dV represents the diffusivity from the grain, so from the volume. And then B is the Burgers vector, sigma of course is the applied stress, T is the temperature, K is the constant, and D is the grain size. So you see, if you increase the grain size, then the creep rate is going to decrease. Okay, and this happens at comparatively higher temperature in diffusion creep. So we know that the stress value is less than, so the normalized stress value is less than 10 to the power minus 4, and this regime of creep can be divided in a part where the diffusion takes place from the grain, and that is called Nabarro-Herring creep because that was discovered by Nabarro and Herring. And then the second part, which happens at a comparatively higher stresses, where the it happens at lower temperature. So at lower temperatures, atoms are not able to diffuse through the grain, but grain boundary, those are, because they are high temperature region and they have no constraint of having a certain atomic position or crystal structure. So that allows the atomic diffusion to be very fast. And therefore, at lower temperature, the predominant diffusion will be taking place on the grain boundary, and therefore the creep, so a steady state creep rate is a function of the diffusivity at the grain boundaries. And here you see that if you increase the grain size, the creep rate will decrease to a larger extent in comparison to a Nabarro-Herring creep, because the exponent here is 2 and here is 3 for the grain size. Okay, so if you increase the grain size, the creep rate will decrease. Okay, this reason is because if you increase the grain size, then you are decreasing the grain boundary area. So this diffusivity is constant, but the overall diffusion will decrease if you increase the grain size, and that's why the creep rate will decrease. So if you plot this normalized strain rate versus normalized stress, then you get this kind of curve. And power law creep is followed in this range of stress, which we have discussed already, right? And power law breakdowns when you go at a normalized stress value higher than 10 to the power minus 3. So this is just to explain you that in different levels of temperatures and stresses, there are different mechanisms involved. And these mechanisms will have different activation energy, and that is why we get a different slope when we plot the stress rupture data. Because obviously, the stress rupture data is a very extensive creep deformation, and we can see the difference in the steady state creep, which is the minimum creep rate. So obviously, in a stress rupture profile, the effect is going to be even larger than this. Okay, so again, this is a little bit of detail on the Kubel creep and Nabarro-Herring creep, which we will not discuss much. And the grain boundary sliding we have already discussed before. This is again in comparison to homologous temperature and stress. You can plot the region. So at which ratio of temperature versus melting point, so that is at which value of homologous temperature and which value of stress, which kind of mechanism is predominant can be described by such diagram, which is called deformation mechanism map for creep. So that was all, and we will discuss once we have a crack in the system in our next part of the lecture. Okay.